Welcome to when the root test fails. So recall, if we have the limit as n goes to infinity of a sub n to the 1 over n is equal to 1, then the root test cannot determine whether we have convergence or divergence. So then the root test cannot determine whether the series that is the sum from n equals 1 to infinity of a sub n converges or diverges. So for example, let's use the root test to determine the convergence of the sum from n equals 1 to infinity of n plus 5 over n plus 2, all raised to the n. So here our a sub n would be n plus 5 over n plus 2, all raised to the nth power. So we have the limit as n goes to infinity of a sub n raised to the 1 over n is the same thing as the limit as n goes to infinity of n plus 5 over n plus 2 raised to the nth, and then that whole thing raised to the 1 over n. Raising to the power of n followed by the nth root just cancels out since we're dealing with positive bases. So this just becomes the limit as n goes to infinity of n plus 5 over n plus 2, which is simply equal to 1. Now note, this n plus 5 over n plus 2 is always going to be larger than 1 since the numerator will be smaller than the denominator for n greater than or equal to 1. So note, n plus 5 over n plus 2 will be greater than or equal to 1. In fact, it's just greater than 1 for n equaling 1, 2, 3, etc. So that means that n plus 5 over n plus 2 raised to the nth power will also be greater than 1 for n equaling 1, 2, 3 on forever. Okay. So what that means then is that our a sub n are all trapped above 1. And of course, the sum from n equals 1 to infinity of 1 diverges. So that means that our sum from n equals 1 to infinity of n plus 5 over n plus 2 raised to the nth also diverges. So in this case, we could kind of tell, but you can see here that if we were, if the limit is coming from above 1, we clearly have this divergence, right? Because essentially, we're just adding on numbers bigger than 1. But if the limit were coming from below 1, then it's hard to tell, right? What exactly is going on. If the limit is coming from below 1, it may diverge, it may converge. There's a whole bunch going on. So the limit equaling 1, we get a bit of a confusing mess here. And of course, if the limit's kind of going back and forth above and below 1, we also get some confusion. So this was a case where it was very clear. We could tell, okay, each of the individual terms will be bigger than 1. So we're adding on a bunch of sizable pieces. This series must diverge. All right. So that is cases where our root test is not, or a case where a root test is not particularly useful. One thing that is extremely unhelpful in the root tests is factorials. So just as a side note, note exponentials are great with root tests. As we just saw here, the exponential can just essentially be canceled out. Factorials are much more annoying. So factorials do not work very well with root tests. Polynomials, you can play the similar trick I did in the previous video with having to take the limit and do L'Hopital's rule, etc. But again, or rational functions. But factorials do not come in handy with root tests. Exponentials, though, are great. All right, in the next videos, we'll move on to alternating series and sort of more room we have to play with once we allow for positive and negative, and specifically just alternating sign in our series.